These are the lesson 6.2 notes on representations of functions. I left off that part, so you need to go ahead and label it that it's lesson 6.2. We did not do a set of notes on 6.1. We're just going to do the workbook page. The most important idea from 6.1 is this, that a function is a relation that pairs each input with exactly one output. So the nice thing about chapter 6 is that it's fairly easy. It is all information that you already know. It just adds some new vocabulary. So the new vocabulary that we're adding is functions. So we're going to start talking about equations as functions, okay? And in the section 6.1, they introduce a mapping diagram, and I'll show you an example of that in this set of notes also. But the big idea was that in a function, you have a graph where each input, that's the x value, pairs up with exactly one output, which is the y value. I'm going to draw a couple of little graphs over here to show you what that means. So you could have, let's do like that, and we're going to graph some things. Not everything that we graph is going to be a line, all right? If you have a line, then each x is automatically paired up with one y, okay? So if it's a line, it's a function. But there are some things that aren't lines, right? You could graph something that looked like that. It could look like a parabola. If you graph this, I can see that as I go over on the x-axis, every time I go over x, I can come up and I'm just going to touch. Let me get a different color pen. If I come over a little bit and then I go up, I'm only going to touch the y in one place. And I go over here and I go up and I'm only going to touch the y in one place. And I go over here and come up and I only cross the y in one place. So each x has one y. And this is a function. But what if our graph, instead of looking like a U, what if it looks like a U laying on its side? What if that U is rotated? Now when I go over to an X, I can come up and it's going to touch the Y there. But then it comes up and there's another Y value that goes with that X. And over here, there are also two Y values that go with an X. This time, there is more than one Y for each X. This is not a function. Okay, so that's pretty much what we covered in lesson 6.1. That's why I decided that we did not need a whole set of notes to cover that little bit. So things that have one y for each x, that's a function. More than one y for an x, not a function. All right, so then let's look at the key idea. So they have this graphic, we call it a function machine, where the function rule is the equation, and then the x value is the input, and that is the independent variable. And then the thing that comes out, the output, is the y, and that is the dependent variable. All right. A function rule is just an equation that describes the relationship between the input, which is the independent, and the output, which is the dependent. And now we'll have some practice writing that. You'll find this very challenging, I'm sure. Write a function rule for the output is 5 less than the input. Well, I know that the output, that's the y, is equals 5 less, that's subtraction, but it's 5 less than the input. And the input is the x. If I want to have 5 less than something, then I need to put the x value first and then subtract 5. Right? So it's not that it's hard, it's just new language that you have to think function language instead of equation language. Okay. And write a function rule for the output is the square of the input. Again, the output, that's the y, is equal to the square of the input. So I'm going to take the x value, which is the n, and square it. Okay, and then you're doing a function rule for the output is 1/4 of the input. All right, example 2. Evaluating a function. What is the value of y equals 2x when x is equal to 3? You have to substitute 3 in for x and figure out what y is. So do the math. 2 times 3 is 6, plus 5 is 11. But the important thing is the language. So we're looking at what is the value of that function at x equals 3. When x is equal to 3, y is equal to 11. So when x equals 3, y equals 11. You do not have to write all of that out every time. You just need to put the value for y. When you substitute for all of these, you're going to substitute in y equals 5. Okay. Down at the bottom, there's just a nice graphic to help you kind of put those pieces together. So a function can be represented by an input-output table and by a graph. The table and the graph below both represent the function y equals x plus 2. So this is very similar to what we did in Chapter 4, Section 4.2, when we had the graph or the equation, and then we made the table, and then we made the graph, and we looked at how all of those pieces were related. Right? So that you choose some values for x, substitute that into the equation that generates the value for y, which then gives you your ordered pair, and then you can graph from the ordered pairs. By drawing a line through the points, you graph all of the solutions of the function y equals x plus 2. And I think, hopefully, we know by now that all of the solutions are on the line and everything on the line is a solution. Okay, so now we'll do one practice. Graphing the function y equals negative 2x plus 1 using the inputs of negative 1 and 0 and 1 and 2. And so when I substitute negative 1 in, I've got negative 2 times negative 1 is 2. 2 plus 1 is, oh, I'm supposed to write that all out. And then this is negative 1, 3. This is just where you show your math. Okay, positive 2 plus 1 is 3. Okay, and then we'll do negative 2 times 0 plus 1. This is the y-intercept. So when x is equal to 0, then y is equal to 1. And then negative 2 times 1. Negative 2 plus 1 is negative 1. And negative 2 times positive 2 plus 1. Negative 4 plus 1 is negative 3. Okay, and then we will plot points. Let's see. I've got x values from negative 1 to 2, and I've got y values from negative 3 to positive 3. So I think I need to do it kind of here in the middle. Hopefully that will be right. Let's see. So if I go back negative 1 and positive 3, 1, 2, 3, 0, 1, positive 1, negative 1, and positive 2, 1, 2, negative 1, 2, 3. And whew, thank goodness, it looks like I did not make any mistakes with my calculations because those appear to be in a line. If I'd had some wonky point over here, that would have meant that I added or subtracted wrong. Probably a sign error. Isn't that what usually happens? Okay, draw your line. Does it ask us to do anything else? No, it doesn't. Can you find the slope easily? Why, yes, you can. Let's go ahead and put them down. The slope and the y-intercept. We know that the y-intercept is at positive 1. And let's see, the slope, I've got the change in the y is, I counted everything by ones, so the change in the y was going down 2, and the change in the x, when I go down 2, I go over 1. So my slope is negative 2. It's going down. You don't have to find the slope every time, but it's good practice. Right, and then you have 2 where you are graphing the equation. You're going to have to write a little small there. You can squish your table in wherever you can. And then the last problem is that real life application. The problem says the number of pounds, P, of carbon dioxide produced by a car is 20 times the number of gallons of gasoline, G, used by the car. Write and graph a function that describes the relationship between G and P. So when I'm looking at G and P, I think that the pounds depends on the gallons. So P must be my dependent variable, which is the Y. So I'm going to write it as P is equal to, and it's 20 times the gallons. So P is equal to 20 G. And then I'm going to choose some values. Right. Let's see. We'll do G. And then the expression. And then P. And then the ordered pair. Seems weird to write an ordered pair like that, doesn't it? Okay, and then we'll put the gallons on the x-axis and pounds on the y. I'm going to choose some fairly small numbers for my gallons, like 1, 1, and 2, and 3. So 20 times 1 is 20. 20 times 2 is 40. And 20 times 3 is 60. So we're going to graph 1, 20, 2, 40, and 3, 60. And so these are really small numbers, so I'm going to count by ones. My x-axis. I can see that I'm all in quadrant 1 because everything is positive, and it makes sense to count by 10s or 20s. Let's go ahead and count by 10 so we can stretch it out a little bit. 10, 20, 30, 40, 50, 60. All right. Over 1, up, 20, over 2, up, 43, 60. So just looking at that, is that a proportional relationship? Is that a line that goes through 0? Does it make sense that that would be proportional and that that line would go through 0? If you don't burn any gallons of gasoline, will you have any pounds of carbon dioxide? No gasoline means no pounds of carbon dioxide. So in this problem, it makes sense that the y-intercept would be 0 because it is proportional. All right, then you have a similar problem where for a truck, because the truck is bigger, it's going to make P is going to be 25 times G. So a little practice there. And then the very last thing is just another summary. It's even the same equation as the other key idea, but it has the mapping diagram. This was the other thing that was in lesson 6.1, and it was just showing another arrangement of these are the inputs and the outputs. So there's your ordered pair, and showing that if each input maps to only one output, then it is a function. So it's just another way of representing the information, right? That's what a mapping diagram